Good morning everybody, myself Raghubir Singh, lecturer in Civil Engineering from Pandit Jagatram Government Polytechnic Colleges, Sharpur. Today in the subject of fluid mechanics, we will discuss a very interesting topic of Bernoulli's theorem and its applications. Let us have a look what are the different contents of today's lecture. We will start up with different types of fluid flow, in the definition of discharge, what is continuity equation. Then we will see three different type of energies and their respective heads of an ideal fluid. The three energies: potential energy, kinetic energy and pressure energy, and the respective heads: the pressure head, kinetic head and potential head. Then the topic, today's topic, the Bernoulli's theorem. What is it? What are the assumptions made by Dr. Bernoulli? What are the limitations of this Bernoulli's theorem? And lastly, we will have a look on different applications of Bernoulli's theorem. Three of the applications we will discuss today: the Venturi meter, Orifice meter and Pitot tube. So starting with the types of fluid flow. Now the fluid in motion depends on various fluid properties like temperature, density, velocity and pressure. These are four different fluid properties on which the fluid in motion depends, and based on these properties the fluid can be classified as, first, steady and unsteady flow, secondly the uniform and non-uniform flow, and thirdly laminar and turbulent flow. Coming to the first one, the steady flow. The steady flow is defined as the type of flow in which the fluid properties like pressure, density and velocity at a point do not change with time. This is important. All these properties are not changing with time. So mathematically we can write it as delta V upon delta T equal to 0. It is not changing. The velocity is not changing. Delta P upon delta T is equal to 0. Once again, pressure is not changing. And delta rho upon delta T is equal to 0. The density is not changing. So all these properties are not changing with time. So such type of flow is called steady flow. And one of the example is the flow through a pipeline under constant head. In our day-to-day life, look at this picture. It's a picture of an Ayurvedic technique called Sirodhara. Now if you have a look on this part, the oil is just falling on the forehead of this person. So the flow from this particular vessel is a steady flow. Since it's not changing with time, most of the time it remains constant with time. It doesn't change. Coming to the unsteady flow. The unsteady flow is defined as the type of flow in which the fluid properties like pressure, density and velocity change with the time. It is just the opposite of steady flow. All these properties are changing with time. So mathematically we can write delta V upon delta T is not equal to 0, delta P upon delta T is not equal to 0, and delta rho upon delta T is not equal to 0. All these three properties are changing with time. So once again, an example of unsteady flow: the flow through a pipeline when a valve is opened or closed gradually. Or just take an example of a small tap in our home. Whenever we close a tap in a kitchen or in a bathroom, if we suddenly close it or just open it, the flow which we observe is the unsteady flow. Let's have a look on this diagram also. In the first part, the flow is steady. As you can see, there is a steady behavior here, and slightly it's changing to the unsteady one. And in the fourth one, if you compare the first stage and the fourth stage, the first stage is the steady flow, whereas this flow has become unsteady. So this is a diagrammatical representation of the steady flow changing into unsteady one. Coming to the uniform flow is that type of flow in which the velocity of the flow of fluid is constant at any section in the path of flow of fluid. So here we are concerned with velocity part. It remains constant at any section. Mathematically, we can write uniform flow as delta V upon delta S is equal to 0. So here T is constant. This is important. T is constant in the uniform flow, where this delta V is the change of velocity and delta S is the change in the displacement. Once again, an example of uniform flow: the flow of water through a pipeline of uniform diameter. It means the diameter remains the same throughout. If we have 2-meter pipe, 2-meter diameter of pipe, and if it remains same throughout, the flow through that pipe can be considered as the uniform flow. You can have a look in this particular channel. This is a good example of uniform flow. The non-uniform one, it is that type of flow in which the velocity of the flow of a fluid is not constant at any section. So it is just opposite of uniform flow. In this particular flow, the velocity of the flow is not constant. So delta V upon delta S is not equal to 0, and the terms are same as in the case of uniform flow. So taking an example of non-uniform flow, the flow of a water through a pipeline of variable diameter. Variable means changing diameter. So if we have a pipeline, one side of it, if it is 2 meter in diameter, and the other side it is 3 meters in diameter, so we can say the flow through that particular pipe is a non-uniform flow. Now coming to a very important flow called the laminar flow. What is a laminar flow? A flow is said to be laminar if each particle fluid has a definite path and the path of one particle does not cross the path of any other particle. There is a definite path and the particles are not crossing each other. It is also called streamline flow or viscous flow. So before moving to these examples, I would like to discuss this example of a kitchen sink. Now in this kitchen sink, this is a swan type of a tap, and as you can see, the water is coming out of it. Now if you look at this flow is laminar flow. This particular flow is a laminar flow. Why? Because this flow has a definite path. Secondly, if you observe it closely, the particles are not crossing each other in this flow. So it's a very good example of laminar flow which you observe daily in your kitchen. Some more examples of laminar flow: the flow of blood in veins and arteries. So in our bloods and veins, in our arteries and veins, we most of the time observe the laminar flow, except of some sudden cases of blood pressure. And groundwater flow is once again a good example of laminar flow. So this is one very important type of flow called the laminar flow. Now the turbulent one. What is a turbulent flow? A flow is said to be turbulent if the fluid particles do not have a definite path. Once again, it is reverse of laminar flow. In the laminar flow, we have definite path, whereas in the turbulent flow, the fluid particles do not have a definite path, and the path of one particle crosses the path of other particle during flow. As you can see, this smoke coming out of this jet aeroplane, and after releasing this smoke out of it, you can observe there is a mixing of particles here. They are crossing each other. There is no definite flow in this pattern. So we can say this smoke coming out of this jet plane is a very good example of turbulent flow. Now this turbulent flow is also called non-laminar flow. Since it is reverse of laminar one, so it is also called non-laminar flow, and the fluid particles are moving in a zigzag way. There is no definite pattern here. So this is a good example of turbulent flow. One or two more examples of turbulent flow: the flow of a river water. You must have observed that in a river the flow is never laminar. Most of the time it is turbulent in nature. And the flow of a petrol through a pipeline, it's again a good example of turbulent flow. So these are two different type of flows, the laminar one and the turbulent one. Now look at this picture. In this particular clip, you may observe the change of laminar flow into the turbulent flow. Now this is the same tap and the same sink which you have observed in the laminar flow, this one. Now if you introduce a spoon here, as there is a zoom view of it, if you introduce a spoon in between, then you can observe from here to here the flow is laminar, and after introducing this spoon the flow has become turbulent. So it's a good example of changing of laminar flow into the turbulent one. Now coming to a very basic definition, discharge. You must have listened to this term, discharge. What is a discharge? Discharge can be defined as the quantity of a fluid flowing per second through a section of a pipe or a channel. So it is mainly concerned with the quantity flowing per second. So it's generally denoted by English alphabet capital Q. Let A is the cross-sectional area of any pipe, and V is the average velocity of the liquid. Then discharge can be written as area into average velocity. So Q is equal to A into V. So this is a formula for the discharge. And if you look at the units of discharge, as we know, the unit of area is meter square, and that of the velocity is meter per second. So just multiplying these two units, we will get a new unit for the discharge, meter cube per second. So the units, SI units of discharge is meter cube per second. Coming to a very important equation called the continuity equation. Now it's concerned with a very important principle called conservation of mass. The continuity equation states that if no liquid is added or removed from the pipe in any length, then the mass passing across different sections shall be the same. Repeating it once again, if no fluid is added or removed from a pipe in any length, if you have a pipe of any length and you are not adding or removing any liquid of it, then the mass passing across different sections shall be the same. The mass is not going to change. And this equation, as I told you earlier also, it is based on the principle of conservation of mass. So mathematically, continuity equation can be written as discharge of the one section is equal to discharge of the other section. A1V1 equal to A2V2. So this is the equation for the continuity equation. Now look at this demonstration. If you have a pipeline from here to here, it has larger diameter, and from this joint till here, for the section 2-2, we have smaller diameter. So we have two sections in a particular pipeline. If V1 is the average velocity at this section, and A1 is the area of pipe of this section, and rho 1 is the density at this section, and similarly V2, A2 and rho 2 are the values for this section 2-2, then the total quantity of fluid mass passing through section 1-1 is rho 1 A1 into V1. This is the formula for the total quantity of fluid mass. And the total quantity of mass passing through section 2-2, it is rho 2 A2 into V2. And we have just seen the law of conservation of mass. According to it, this total quantity of fluid mass in the section 1-1 will be equal to the total quantity of fluid mass through section 2-2. So you can observe, according to the law of conservation of mass, these two should be equal. But very important, for incompressible fluids, this rho 1 is equal to this rho 2. So just neglecting these two, if these are equal, we will get a final equation of continuity equation. It is A1V1 equal to A2V2. So this is the final equation for the, which I should say it's the continuity equation. Now look at the energies of an ideal fluid. The energies of an ideal fluid, we have three types of energies. The kinetic energy denoted by capital E, potential energy denoted by capital U, and pressure energy P. Based on above three types of energies, we have three different type of heads: kinetic head, potential head and pressure head. Now if you remember what is a head, head is the specific measurement of a water pressure above a datum. If you have any datum or a reference line, reference point, from that particular reference line, if you have some specific measurement or some height, it is the head or the column of a water or of any fluid. And we most of the time we measure this head in centimeters, millimeters or in meters sometimes. So we have three energies and three heads. We will look at it one by one. The kinetic energy. Now the kinetic energy of a fluid particle is the energy which it possesses due to its motion or velocity. So kinetic energy is concerned with the motion or velocity. Taking an example, as you can see, this is a seashore. The waves are striking at the seashore, and these are a very good example of kinetic energy. The waves striking at the seashore. And related to the kinetic energy, we have kinetic head. Now keep in mind, this kinetic head is also called the velocity head. So both are one and the same thing, kinetic head or velocity head. Now what is it? It is the kinetic energy of a fluid per units of its weight. So kinetic energy upon weight is what we call kinetic head. Something more about it. Let us suppose the mass of a fluid particle is mkg and the velocity of the flow of the fluid is v meter per second. So the kinetic energy of the fluid particle E can be written as half mv square joules. So it is the unit of kinetic energy. Joules or joules, we often say half mv square, m for the mass and v for the velocity. And this 1 joule, it is equal to 1 kg meter square upon second square or 1 Newton meter. So 1 joule is equal to 1 Newton meter. Now if the weight of a particular fluid particle is W, capital W, which is equal to m into g, the mass into acceleration due to gravity, then kinetic head or the velocity head can be written as I just told you, it is kinetic energy upon weight. As you have seen in this definition also, kinetic head is the kinetic energy of a fluid per unit of its weight. So, kinetic head or velocity head is E upon W. Now, what is E? E is half mv square, as you can write here also. What is W? It is equal to mg. So, just put the values of E and W, and just cancelling this m, we get an expression for kinetic head. This 2 will come in the denominator. So, we will get v square upon this 2 into g. This will get cancelled, m and m. So, final expression for the kinetic head or the velocity head is v square upon twice g. G is the acceleration due to gravity, meters of the fluid. So, this is first type of energy, kinetic energy and kinetic head. Moving to the second one, the potential energy. Now, potential energy is concerned with the position. The potential energy of a fluid particle is the energy which it possesses due to its position. As you can see, a person is just resisting this particular stone. Now, here we are concerned with the position of this stone. So, we will observe a potential energy here. So, potential energy is concerned with the position part, and related to this potential energy we have potential head. So, what is potential head? It is potential energy per units of its weight, just like kinetic energy. Kinetic head, it is kinetic energy upon weight. So, here the potential energy is potential head is potential energy upon weight. Look at the expression. If m is the mass of the fluid particles in kg, if z is the height of the fluid particle above datum level. Suppose if you have any reference line or datum level, we have a height of a particle z meters, then potential energy of the fluid particle u is given by mg into z. So, this is the expression for potential energy. Weight, we all know it is equal to m into g. So, to get the expression for potential head, we will divide u by w. It is potential energy upon weight. So, putting the values of u mg into z and the value of w m into g, just cancelling these two expressions m and g, we will only remain with the z part. So, the potential head is equal to nothing but only z. So, this is the expression for the potential head. V square upon 2g is the kinetic head and z is the potential head. Now, remains the third one, pressure energy. The energy possessed by the fluid particles by virtue of its existing pressure. As you can observe this pump, centrifugal pump. In this pump, the energy which we observe is the pressure energy. So, repeating it once again, the energy possessed by the fluid particles by virtue of its existing pressure is called pressure energy. And regarding pressure head, it is in the same pattern of the other two. It is pressure energy upon weight. So, moving to the expression, pressure energy capital P in Newton per meter is pressure intensity into volume. Now, pressure intensity is small p, V is the volume, and we all know there is expression of specific weight or weight density. Small w is equal to total weight upon volume. So, from this expression we will put the value of volume as w upon small w, and the pressure head of the liquid will be this pressure energy upon w. So, this will get cancelled and we will remain with p. This will come to the denominator. So, it will be p upon w. So, pressure head capital P is given by small p pressure intensity upon w. So, we have seen three different type of energies, three different type of heads. The kinetic head v square upon 2g, the potential head z capital Z, and this pressure head which is small p upon w. Now we will combine all these three heads and we will get an expression for the total energy or total head of a liquid particle in motion. And the total energy is given by Z, the potential one, V square upon 2g, the kinetic one, and P upon W, the pressure one. So all these three type of heads, if we combine these three, sorry, so we will get a expression for capital H, the total head, which is Z plus V square upon 2g plus P upon W. So this is the addition of three different type of heads. Now coming right to the main theorem which we will discuss today. The name of our lecture is also regarding Mr. Bernoulli's. In 1783, Dr. Daniel Bernoulli gave a theorem called Bernoulli's theorem. Now what is this theorem all about? This theorem states that the total energy of the fluid particle remains the same for an ideal incompressible fluid flowing from one section to the another section in a continuous stream. So discussing it in other language, if you have one section here, section 1,1, and section 2,2, which is larger one, according to Bernoulli's theorem, if the fluid passing through this particular section is incompressible fluid, then the total energy which is here, it will remain same here also. So this is the basic thing which Dr. Bernoulli wanted to say, that the total energy remains same in both these sections. Now Bernoulli's theorem can be derived from the principle of conservation of energy. You must have studied this principle in your previous classes, that what is the principle of conservation of energy? That energy can neither be destroyed nor be created, but it can be transformed from one state to another. This is the principle of conservation of energy, and Bernoulli's theorem can be derived from this principle. And mathematically we write Bernoulli's theorem as P upon W plus V square upon 2g plus Z. What is this? This is the expression which we have just seen, the expression for the total head, adding all the three different heads. Now the addition of these three heads is equal to constant according to the Bernoulli's theorem. So this is the mathematical expression for the Bernoulli's theorem, that the sum of all the heads, the pressure head, first one, the kinetic head or the velocity head, second one, and the potential head, third one, their addition will be constant, or I should say the energy remains constant throughout in a one section, or it may be in the another section in a stream. Now there are certain assumptions made by Bernoulli's before this theorem. The first assumption is the flow is steady and continuous. The second one, the flow is along a streamline. Then the flow is ideal and incompressible. The velocity is uniform over the section. It's not non-uniform, and no external force is acting on the fluid except the force of gravity. So these are the assumptions made by Bernoulli's theorem, but there are certain limitations also. The first is the loss of energy due to the pipe friction is not considered in Bernoulli's theorem. It is neglected. So this is very important. This is the limitation of Bernoulli's theorem. Pipe friction is not considered. It is neglected. Secondly, the loss of energy due to turbulency, it is also not taken into account. The second limitation of Bernoulli's theorem. Thirdly, Bernoulli's theorem or the Bernoulli's equation does not take into consideration the loss of energy due to direction. There is always loss of energy whenever there is a change in the direction of a liquid. So it is again not considered in the Bernoulli's theorem. So these three are the limitations of Bernoulli's theorem. Now, in assumptions, the velocity of the liquid particle at any point across a section is assumed to be uniform. If you remember, it is uniform, but the velocity of the liquid particle is maximum at the center of a pipeline, and it gradually decreases towards the walls of the pipe. In the assumption, it is considered uniform, but